Hi everyone, and welcome to week 6, Deepen Your Learning. This week we'll be discussing radioactive decay, which might conjure images like this one of radioactivity and danger, but in reality, radioactive decay can be incredibly useful. First, a quick definition of radioactive decay. Radioactive decay occurs when radioactive elements, such as uranium, decay into particles, energy, and other elements. This is a natural occurrence, and it also happens with common isotopes of things like carbon. So it's not just happening with crazy and dangerous radioactive things, but it's happening with many different elements. Let's look at an example of radioactive decay with carbon. Now, I have a fossil that looks exactly like this sitting on my desk right now. It's dated to 50 million years old, and the reason why we were able to figure out how old this fossil is because of radioactive decay of carbon, also known as carbon dating. Normal carbon is carbon-12. It has 6 protons and 6 neutrons. When you have a radioactive isotope of carbon, it has 6 protons and 8 neutrons, making it imbalanced and heavy. It doesn't like to stay in that imbalanced state, and so it will decay over time into nitrogen-14, which is a stable form of nitrogen. That takes about 5,730 years for one half-life of carbon-14 to decay into nitrogen-14. Now let's look closer at half-lives. A half-life is the amount of time required for a quantity to fall to half its value. So if I have some amount of a radioactive element, a half-life is how long it takes for half of that to decay. Or another way to say that is a half-life is the time that is required to produce equal proportions of parent, or the original atoms, and daughter atoms from an initial state composed entirely of parent atoms. And this chart here on the left shows you how after each half-life elapsed, we'll have half of what was left after the previous half-life, and this continues on. Now an example of half-lives. So we're going to say in this example that all the dark gray boxes, after one half-life has elapsed, you can now see that half of the boxes are a lighter gray and half of the substance has decomposed into a different atom. Now 2 half-lives have passed. We had 18 gray boxes that were left dark gray. Now there are only 9, so half of what was left decomposed. Now 3 half-lives have passed. There were 9 boxes remaining, and 4.5 of those have now decomposed. And with a 4th half-life, 2.25 boxes have decomposed. This can go again on and on and on. We can use half-lives in really cool ways, and one way is with this reddish rock here called a zircon. Zircons are found in samples primarily from Australia, and we use something called uranium lead dating, which is where uranium decays into lead, in order to date these rocks because they have been around much longer than samples that we would use carbon dating for. Uranium has a half-life of about 4.5 billion years, so samples of uranium will stick around for a very long time. Because of uranium in zircons, we have been able to date the age of the Earth to around 4.6 billion years. I think radiometric dating is a great example of a type of science that is a gift to us. Radiometric dating allows us to figure out how old things are. Maybe organisms that lived on Earth before, or even the age of the Earth. And those things are far beyond the perspective of humanity. And so I'm really grateful that we have science like radiometric dating. They give context to the history of the Earth and the history of the universe far beyond what we would be able to have on our own. And I think that types of science like that are gifts from our Heavenly Father.